Today we're going to continue looking at section P.6, which is rational expressions. So today we're going to continue performing operations on rational expressions as well as simplify complex rational expressions. All right, so yesterday we looked at multiplying and dividing. Today we're going to look at adding and subtracting. First, we'll start with the same denominator. So remember, just in general, when you're adding or subtracting fractions, you have to have a common denominator. So when they're already the same, that makes our lives a lot easier because all we have to do is just combine the numerators and we keep the denominator the same. But after we do that operation, we always need to make sure that we are simplifying as much as possible. So let's take a look at this example. Notice that it says to subtract. We've got x over x plus 1 minus 3x plus 2 over x plus 1. So notice that my denominators are the same. They're x plus 1. Had it been factorable, like always look to see if you can factor your denominator first. So in this case, x plus 1, there's no GCF to take out or anything like that. So I don't need to worry about factoring. But because it is the exact same fraction, or denominator, I get to make it one big fraction. So I get to keep that denominator as x plus 1. If you want, I would maybe keep it in parentheses for right now. But then this is where you have to be careful. Because I'm subtracting, it's x minus, but then I am subtracting not just one term, but two terms. So when there's more than one term after the subtraction sign, put it in parentheses so then we make sure that we do not lose the operation completely. I want to distribute that negative so I can start combining like terms in my numerator. So we'll now have x minus 3x minus 2 on the top. This is still all over x plus 1. We've got some like terms, so I'm going to combine x minus 3x is negative 2x minus 2, and that's still all over x plus 1. So there's nothing left for me to combine in the numerator, but now I want to see if I can simplify. And so remember, the steps for simplifying is to factor as much as possible. The denominator we already know is not factorable, but the numerator in this case is. Notice that they both have something in common. They have a negative 2. If I factor that out, that leaves me with x plus 1. And so notice that, hey, I do have something on the top that's also on the bottom. That is going to simplify, and that's why my final answer ends up just being negative 2. So if it was addition, you wouldn't really have to worry about putting that second numerator in parentheses because we could just combine like terms right away. But it's very, very important when we're doing subtraction that you subtract the entire second numerator in order to correctly combine your like terms. All right, let's talk about adding and subtracting with different denominators. So in order to add or subtract, we need to have a least common denominator. So if the denominators have no common factors, then their product becomes the new denominator. Okay, so remember products, multiplication. So in the past, when we had a fraction where maybe one denominator was 3 and one denominator was 2, we multiplied them together. 6 was that LCD. So same idea, but now we're just dealing with polynomials as our denominators. It's important to note that if the denominator changes, the numerator must change as well. So I can't just change the bottom. I have to make sure the top is also changed in order to make sure that we're not making the problem a completely different problem. We have to keep that original problem the same. All right, so let's take a look at this example. We're going to add x plus 1 over x minus 1 plus 8 over x plus 3. So once again, I'm going to look at my denominators. I'm going to see if I can factor anything as much as possible. X minus 1 is not factorable, and neither is x plus 3. Because those are different denominators, we need a least common denominator. When you have these two binomials, but they are completely different binomials, that's what the direction said. We are going to make the product the LCD. So that means x minus 1 times x plus 3 is the least common denominator. Now, don't actually multiply those two binomials together. I want to keep everything as factored as possible because remember, at the very end of this whole entire process, I need everything factored to see if I can simplify. So that means my new denominators become that LCD. So x minus 1 times x plus 3 for both of these. My original numerator on the top is x plus 1. However, because I technically multiplied that first denominator by x plus 3, if I do it to the bottom, I have to also do it to the top. So that's why x plus 1 also needs to be multiplied by x plus 3. Same idea with that 8. I start with an 8, but because my original denominator was only one binomial and now it's 2, I multiplied that by x minus 1, which means if I do it to the bottom, I'm going to do it to the top. So that's why I need to have 8 times x minus 1. All right, so because they now have the same denominator, I get to write it as one big fraction where the denominator is that LCD. What I'm going to do though, in order to add these two numerators, I need to have everything not factored. So it's the numerator that we first have to multiply, and so that way we can combine like terms, but never multiply out the denominator. So this first numerator, I'm going to multiply those two binomials together. So x times x is x squared, x times 3 is 3x, 1 times x is 1x, and 1 times 3 is 3. Over here in the second numerator, I just have to distribute that positive 8 because it's an addition problem. I don't have to worry about that 8 changing signs. So 8 times x is 8x. 8 times negative 1 is negative 8. Once I multiplied out those terms in the numerator, now I can combine my like terms. There's nothing to combine with the x squared. We've got a 3x, a 1x, and an 8x. So that's going to give us 12x. And then we have 3 and negative 8, which gives us negative 5. My denominator, like I said, do not factor that or multiply it out, I mean. So now that I've combined like terms in the numerator, I want to see if I can simplify. So can I factor? Is there something that multiplies to negative 5 but adds to 12? And my answer is no. So because that numerator is not factorable, we are done. This is my final answer. But had it been factorable, we would, and then we'd see is there anything in the numerator that's also in the denominator that we'd be able to simplify. Okay, let's look at a subtraction problem. We've got x plus 2 over 2x minus 3 minus 4 over x plus 1. So I look at my denominators and I first want to ask myself, is anything factorable? 2x minus 3, there's nothing to factor there. X plus 3, there's nothing to factor there. Because those are two very different binomials, that means just putting those two together as a product is going to be the least common denominator. So that means that I want to have 2x minus 3 times x plus 3 for both of these fractions. Notice that my original numerator, x plus 2, is no longer just the numerator for the first fraction. My original fraction, the denominator got multiplied by the x plus 3 to get me the LCD. So if I do it to the bottom, I got to do it to the top. So that's why I then have x plus 3 being multiplied by it. If it helps, I like to change subtraction into adding the opposite. So I'm going to change that subtraction sign to addition, which means then the negative goes with the 4. There's my numerator, but that's not going to stay my numerator because that was just my original numerator. The denominator had to get multiplied by 2x minus 3, which means the numerator does as well. So I have to multiply that negative 4 by 2x minus 3. Once I have fixed my numerators to match my new denominator, I get to write this as one big fraction. So I get to keep the denominator factored. The numerator, though, I want to combine like terms. And so in order to combine like terms, I do need to multiply things out. So I'm going to multiply out the first numerator. X times x is x squared. X times 3 is 3x. 2 times x is 2x, and 2 times 3 is 6. This is why I like to put the negative with that 4. I changed subtraction, so now I know that it's negative 4 that has to get distributed. So negative 4 times 2x is negative 8x, and negative 4 times negative 3 is positive 12. Now I can combine my like terms. There's only 1x squared, but if I look at my x's, I've got 3x, 2x, and negative 8x. Combine those, you get negative 3x. We've got 6 and 12, which is going to add to 18. This is still all over my denominator. So now that I have this like term numerator, I'm asking myself, can I factor any further so then I can see if I can simplify? So can I find two numbers that multiply to positive 18 but add to negative 3? And that would be a no. If that was a negative 18, then I would be able to. But unfortunately, there's nothing that I can factor. So then this would be my final answer. There's nothing I can simplify. All right, so adding and subtracting rational expressions with a different denominator. We've already talked about that, but it's always been the case where they're just two very different binomials and we put them together. But sometimes you're going to have an LCD when all factors are different. So, however, we might have similar factors within those denominators. So we need to think about then taking the highest exponent. So notice that if I'm looking at this example, my denominators are as factored as possible, but notice that I've got an x squared monomial and then an x to the 6th monomial. So I do technically have the same variable. So like it says, when those exponents are different, we have to take the highest exponent. So my least common denominator would be x to the 6th, as well as whatever was left over that they didn't have in common, which is the x plus 2. So that would be my LCD. So when they have similar factors, take the biggest exponent and also take whatever is not in common between those two or three or however many terms. So let's take a look at this example. We're going to add x plus 3 all over x squared plus x minus 2. And we're going to add that onto the 2 over x squared minus 1. So I want to factor my denominator as much as possible. This time they are factorable. X squared plus x minus 2 factors into x plus 2 times x minus 1. X squared minus 1 is x plus 1 times x minus 1. Notice that in these two denominators, they share something in common. So when they both have something in common, that's going to be a part of the least common denominator. You need to take the higher exponent. Well, they happen to have the same exponent. They're both technically just raised to the first power. But now if one was raised to the second power, you take the degree 2 over the degree 1. So because they have the same exact thing, you only have to write that one time. But then you also have to include anything that was not the same. So that means we also have to include the x plus 2 and the x plus 1. So in this case, there are 3 binomials multiplied together to create my LCD. So I'm going to write that. And then remember, we're going to have to fix our numerators to match these new denominators. So my original first numerator is x plus 3. So what is new to the denominator that I didn't originally have? Well, I had 2 factors. I'm missing the third. The third is the x plus 1. So that's what I had to multiply the top and the bottom by. The 2 is now also going to contain a factor with it. If I look at my original denominator and the denominator that I want, we'll notice that there is an x plus 2 that got multiplied then to both the top as well as the bottom. So I get to write that denominator one time. And now I want to start combining the numerators. So I'm going to multiply out the first numerator. That gives you x squared plus x plus 3x plus 3. I'm going to distribute the 2 to the second numerator, and that gives me 2x plus 4. I'm going to combine my like terms. That gives us x squared. We got x, 3x, and 2x. So now that's 6x. 3 and 4 add up to 7. And then my last step is just to double check, can I factor the numerator so then I can simplify this any further? Well, the only way to multiply to 7 is 1 and 7. That won't add up to 6. So it looks like I can't factor any further. So this would be my answer. All right, let's look at the subtraction problem. Once again, I want to factor the denominator as much as possible before I figure out my least common denominator, because these are obviously different denominators. So if I factor the first denominator, it's going to factor into x minus 5 times x minus 5. When it's the same exact factor, it might be best if we think of it as x minus 5 quantity squared, because we do need to look at the biggest degree when we're looking at our different denominators. Because notice that in my second denominator, they have a GCF of 2, which then leaves you with an x minus 5. So notice that they do have something in common. They have an x minus 5, but they have different exponents this time. So remember, I have to take the bigger of the two exponents. So x minus 5 quantity squared has to be that LCD. And then the only thing that they don't have in common is a 2. So that also has to be part of that. So now that I know that that is my least common denominator, I have to multiply the numerator by something to make that happen. If you want, now you can write it as x minus 5 times x minus 5. If you want to just write it as x minus 5 quantity squared, go for it. But notice that the only thing that's missing from the original denominator to the new denominator is that number 2. So that's what gets multiplied by x there. Okay, if I'm subtracting, I'll have my denominator the same. Okay, my original numerator is x minus 4. Notice that what I'm missing here is an x minus 5. Okay, so what I'm going to do now is I'm going to start combining my numerators. So x times 2 is 2x minus, now because it's subtraction and there's more than one thing that comes after it, I'm going to put it in parentheses, but I have to multiply out those two binomials. X times x is x squared. X times negative 5 is negative 5x. Negative 4 times x is negative 4x. Negative 4 times negative 5 is positive 20. And then we still have our denominator. Okay, I can combine like terms in the parentheses of the numerator, but I also then have to distribute a negative. So understand that we'll still have 2x, but now I'll have a negative x squared. This is going to simplify to be negative 9x, but when I distribute the negative, it becomes a positive 9x. And when I distribute the negative to the 20, we'll have negative 20. So one more thing to combine, I have some x's there. So then that's going to give us a negative x squared plus 11x minus 20 all over my denominator. Okay, if I want to try to factor the numerator, I always want my x squared term to be positive. So I could factor out a negative 1, which would then change all of the signs. But then the question is, can I find two numbers that multiply to positive 20, but then add to negative 11? And your answer there would be no. So there's really no need for you to factor out a negative because that's not going to change anything. So this would be my final answer. So pause the video, see if you can subtract these two fractions. Okay, so notice that the first fraction, the denominator had two of the same terms. So that's why I needed to take the higher exponent, even though I saw x plus 4 in the second fraction, I needed to take the two of them. And then there was something different. So then notice how I had to fix the numerator to match my denominator. If you want, you can think of that subtraction sign as adding the opposite. So then I had to distribute a -3, which is why that 12 is negative at the very end there. Combine like terms, I saw that, yeah, I could factor out a 2, but then I couldn't factor anything further. So if you didn't factor out the 2, that's fine, but know that technically you could. We just couldn't go any further. All right, let's talk about complex rational expressions. We have talked about this in the past a little bit. We're just going to review it. Remember, a complex rational expression, which is also just known as a complex fraction, is when you have a fraction inside of a fraction. So numerators or denominators contain rational expressions. So here's just a random example. Notice that there are fractions on the numerator, there's fractions in the denominator. So fractions within fractions, complex fraction. So to simplify, what we're going to do is we're going to find the least common denominator from all the denominators in both the top and the bottom of our big fraction. We'll multiply every single term in the numerator and denominator by that LCD, and then we will simplify. So here we go. We're going to simplify 1 plus 1 over x all over 1 minus 1 over x. So we have to look at the denominators. I see that in the top, there's only one denominator. In the bottom, there's only one denominator. The nice thing about this, they're the same denominator. So that means LCD is just x. So that means everything on the top is going to get multiplied by x. So x is going to get multiplied by 1 plus 1 over x. And in the denominator, same thing. The x is going to get multiplied by 1 minus 1 over x. The whole point is that if I multiply everything by the LCD, there should be no more fractions in the numerator and no more fractions in the denominator. I should just have one overall big fraction. So if I distribute the x on the top, that gives you x plus 1. If I distribute the x on the bottom, that's going to give you an x minus 1. There's nothing to factor on the top and there's nothing to factor on the bottom. I can't simplify that down any further. This would be my answer. Okay, let's take a look at this example. We have 1 over x plus 7 minus 1 over x all over 7. So if I look, I see I have two different denominators. And so when I'm trying to come up with the least common denominator, once again, if those denominators were factorable, factor them. But there's nothing to factor with an x plus 7 and a monomial is not factorable. Since those are two different denominators, then the product would be the LCD. So that means that that is what I'm multiplying everything on the top and everything on the bottom by. So x times x plus 7 is going to get multiplied by 1 over x plus 7 minus 1 over x. And the same thing's happening in the denominator. That 7 in the denominator gets multiplied by the x times x plus 7. Okay, so I'm going to distribute in the numerator. Remember, the whole point is that I should be clearing away the fractions. So with the first fraction, the x plus 7s cancel. And so that leaves you with 1 times x, which is just x. Then I have my subtraction sign. When I distribute that to the second fraction, it's the x's that cancel. 1 in the numerator got multiplied then by x plus 7. So that means we'll have x plus 7. Notice how I still have it in parentheses because I want to be subtracting the whole entire thing from it. The whole denominator is just then this product. I'm going to distribute that negative sign. So that gives me x minus 7, still all over that, now denominator. Notice how I can combine like terms, which then just gives you a -7 on the top and a 7, keep doing that, 7x times x plus 7. You can't factor the numerator because it's just a monomial. The denominator is already as factored as possible. So that's why I did not distribute that 7x. I want to keep everything factored because now notice I actually can simplify. I do have a 7 on the top and the bottom. So that means that I do have to keep the negative on the top. So it's really just a -1. And then that would be all over x times x plus 7. And that would be my simplified answer. Okay, so you try this checkpoint problem, please. All right, notice that with all of the denominators, even though there's a 2 and a 4, 4 is the bigger common number. So that's why just 4x is what needs to get multiplied by both the top and the bottom. That got rid of every fraction. But then notice that even if I tried to factor my numerator, which I could take out a 2, it's not going to then change anything. It doesn't simplify the denominator, which is not factorable. So that would be my answer. Okay, so that's us adding and subtracting as well as looking at complex rational expressions.